I now wanted to say a little bit about some different but related ideas of how we could use natural logic models for doing reasoning about language and doing question answering. So natural logic is an idea that's existed variously for a long time of, can we do logic directly over the forms of natural language? So it's kind of a weak proof theory over surface linguistic forms. So if you look at natural logic, this is really where logic started with Aristotle. So if you've seen Aristotle's syllogisms like Socrates is a man, all men are mortal, therefore Socrates is mortal, that's doing inferences directly over human language. So that's a form of natural logic. The idea was revived by George Lakoff in the 60s, and then it was further picked up and developed by Johan van Bentham in the Netherlands. And so he developed a formalized weak proof theory over surface linguistic forms, but it seemed to us there was nevertheless one that can model many of the common sense inferences that we wish to make. So my former student Bill McCartney first worked on this and developed an extended calculus of natural logic. And so that model was then picked up by a student of Johann's, Thomas E. Card, who formalized a lot of that model. And now we've sort of been looking at how can we use this model for large-scale inference. So what we'd like to do is learn how to reason about the truth of hypotheses based on the facts that we can learn around the world from a lot of text. So for example, we might want to learn what country Obama was born in, or what do cats play with, or where is baseball played. So we're assuming that we have as a resource a large knowledge base. And in many contexts, people assume that that large knowledge base is a structured, formalized, logical knowledge base. But in our case, we're just going to assume the knowledge base is pieces of text that we found around the world. So we read sentences somewhere of a cat ate a mouse and that all cats have tails and all kittens are cute. And we'll just have a big pile of text. In particular, there's no normalization of that text, no claim it's all consistent. And so the hope, nevertheless, is that we can do a middle level of composition and inference to be able to better understand text and to work out the answers to questions. So if you use very shallow IR bag of words models, they're easily thrown off if you just match words and don't understand the sentence context. People have tried to use deep logical reasoning for text understanding, which in theory is very precise, but in practice, the ability to make the inferences you want is normally not there, and you don't have the structured knowledge that you'd like to have. And what we're hoping to do is find a middle ground by treating this as a natural logic inference task. Okay, so this has been work that's been done by my PhD student, Gabor Anjali, in the last couple of years. So we start off with this large pile of text, which we're going to treat as our knowledge base. And then you might think that what we could do was infer new facts from that. And in principle we could, but we have an enormous amount of text and it's probably inconsistent in all sorts of ways. And so we wouldn't really want to try and run inferences over combining all of these facts and seeing what we could derive from them. So instead what we're going to do is the opposite, that we're going to infer whether things are facts on demand from a query. So if we have a query of interest, we think it might be the case that no carnivores eat animals, then what we want to be able to do is run backwards from that query to see what our knowledge base says. And so we're going to do steps here, which are then steps of natural language inference. So from no carnivores eat animals, we can tell that that would be contradicted by the carnivores eat animals, and that this fact would be consistent with a cat eats animals, and that would be consistent with a cat eating an animal, which would be consistent with a cat eating a mouse. And so therefore, if we've got a fact of a cat eating a mouse, that would contradict that no carnivores eat animals. And so that's the kind of style of natural logic inference that we want to do. Of course, we can't expect to get lucky the first time we start expanding things. So really we're going to explore down in a large search, and as we explore down the search, we're going to try and find stuff that matches in our knowledge base. And so the central natural logic inference question is, if I mutate a sentence in some way, do I preserve its truth? So we want to know that if all young rabbits drink milk, can we therefore say all rabbits drink milk? And the answer is no, that's not a valid conclusion. But if some young rabbits drink milk, then we do know that some rabbits drink milk. That is a valid conclusion. And so we want to build a calculus that allows us to do these kind of natural logic inferences. And one of the concerns of that is that we need to understand polarity. So one source of inference we have is set containment relationships between words. So we know that a cat is a kind of feline, is a kind of animal, and that will allow us to make certain inferences. So if we know that some cats drink milk, we know that some animals drink milk. But that, when we can make these kind of inferences, is affected by whether you're in a positive or a negative context. So we also need to know the polarity, the direction a phrase can move in this ordering. So if it's the context that I just said of some cats drink milk, therefore some animals drink milk, we can be sort of moving upwards. But in a negative context, we'd be moving downwards. And what we find is that different linguistic operators like quantifiers respect different polarities. So if we start off with a sentence like all cats eat mice, then the valid inferences in this first noun phrase position are going downward in specificity. So if all cats eat mice, then all house cats eat mice. This position goes up. If all house cats eat mice, then all house cats consume mice, but it does not mean that they slurp mice. And in the final position over here, again, you're allowed to go upwards. So going downwards is invalid, but going upwards is valid. So we had this result that you could infer downward in this position and upward in these two positions and get valid inferences. And so that's understanding the polarity of different positions as to when you could infer upward or downward. Okay, so what's good about using a natural logic proof method like this? A great thing about it is it's actually very computationally fast during inference, so that we don't have a semantics as some kind of logical knowledge representation that's hard to get at with a lot of uncertainty, that all we're using is a straightforward syntactic parse. And our steps of logical inference are just changing a word, adding or deleting a word. It's computationally fast to pre-process. We're just using plain text. And it's a weak logic. It doesn't allow all of the theorem-proving results of, say, first-order predicate calculus, but actually captures most of the common types of inferences that come up all the time and which human readers can be expected to make instantly. Okay, and so that's essentially what we're doing. So we have this big text space, and we'd like to decide which things are invalid or not, and we're starting with what we'd like to improve and doing this search. And so as we search, we're having these steps that we go through. So start with no carnivores eat animals. We consider one-word mutations of that, changing words or adding or deleting. And then we're working out their logical relationship. So this one is these two contradict each other. Then the logical relationship of these two is this one supports this one, and we head on down until eventually we find a fact that we have a piece of text in our knowledge base, and then we can decide what the truth status of our starting out statement or question is. So we've applied this idea to a couple of example problems of common sense reasoning and question answering, and so I'll finish by just telling you a bit about these. So one first set of experiments was with common sense reasoning facts. And so a group at MIT have developed ConceptNet, which was meant to be a sort of a database of common sense facts in a formalized representation, like not all birds can fly, noses are used to smell, music is used for pleasure. And so we thought we could just see whether, starting with the plain text that we had gotten off the internet, whether we could successfully infer those things. So we got a second data set which was then taken from a previous system from the University of Washington. They've worked a lot on open information extraction, of trying to get facts out of web pages. And so we took a collection of extracted facts from their system. We manually filtered it for correctness, and that got a balanced data set, which is pretty easy because the accuracy of their facts is at best 50%. And so for our source knowledge base, in this case, we start with clauses which actually come from a different University of Washington open information extraction system. So we get as our starting point these clauses like Obama was born in Hawaii. And I'll say in a minute how we have a method now for cutting up whole sentences into these shorter clauses ourselves. But here are some results from this system. So one thing we could do is just do direct lookup. So if we're being asked not all birds can fly, true or false, we could just look at our big pile of text and see whether the fact is in that pile of text. And if so, it turns out we get everything right, which reflects the fact that at least for these examples, the correct answer is at least always more frequent than any wrong answers. But our recall is very low. But then we can start using naturally to try and infer answers using natural logic inference steps. And if we do that, our precision goes down a little bit, but our recall goes up enormously, that we're able to quadruple the number of times that we're able to work out the right answer. And so that's really nice. And in particular, if you don't allow answers that direct lookup, naturally can really do almost as well by having to infer an answer. Okay, so that was a starting proof of system, but there was one bit I kind of skipped over, which was I sort of said that our knowledge base was just a big pile of text, but actually the knowledge base for that example, we're using individual simple subject, verb, object style predicates like the cat ate a mouse, which we'd actually gotten from the UW information extraction system, OLI. So what we'd like to do is fully be able to have a knowledge base that starts off with these just complex, nasty, real-world sentences. And so we also did some work for that. And the interesting thing is you can also actually think of this as a problem in natural logic. So what we'd like to do is start off with big, long, real sentences and then get out of it shorter, simple sentences. And the ones that we'd like to get out are the ones that can be supported as natural logic inferences. Okay, so how do we do that? Well, for the syntactic representation that we've been using, this has been using a representation called universal dependencies, which builds on earlier work that we did at Stanford on Stanford dependencies. And so the idea of Stanford dependencies was to give a single level of type dependency syntax that gives a simple human-friendly representation of sentence structure and meaning. Dependency representations of linguistic structure have actually been exceedingly popular and a lot of the development of them has happened in places like Russia, so I hope some of you have seen these representations before. And so these have turned out to be very friendly representations for machine interpretation because they're almost a semantic network. And so the idea then of universal dependencies is to be a version 2 of this that's linguistically better across languages than earlier representations. And so this is a project that a whole bunch of us are working on, and you can find it on the web at this address. Happy to have other people involved in that. So in the context here, what we're going to do is we're going to start with real sentences with their universal dependency syntactic parse done automatically, and we have actually a neural network dependency parser that works very well for that. And then what we're going to want to do is split it up into clauses. And the main trick for that, which we build a simple classifier for, is when we split clauses, we need to add their shared arguments. So when it's born in Hawaii, Obama is a US citizen, we want to not just get out born in Hawaii, but Obama was born in Hawaii. And so we have a supervised learning system which tries to yield entailed clauses. So it goes breadth first down the search tree, and at each point it decides is it a point where it can extract a clause. It could extract a clause providing it fills in the subject of the current clause from a higher argument of a higher clause, or whether it should continue searching downwards, or whether it's gotten below the level of the smallest clause and it should stop. And we're able to train this using the idea of distance supervised training, where we haven't actually labeled sentences for this, but we've just trained it based on things that we know about as good extractions in the past using the OLI data that we classified previously. And so the object, again, is to use the natural logic idea that we can shorten clauses in any way that preserves validity. So from all young rabbits drink milk, we don't want to shorten it to all rabbits drink milk, but from some young rabbits drink milk, we can shorten it to some rabbits drink milk. So in that way, we use natural logic to get these short little snippets of language which is still valid. And so that's sort of the same idea as before, that we're manipulating around modifications and seeing what we can do. As a result of that, we've effectively built our own open information extraction system, where we take whole sentences from the web, we divide them into clauses using our classifier, and then we shorten them using natural logic. And I'm going to finish by presenting two of the things that we've done with that. One is just to use it as an open information extraction system and see how well it works. And then the other is actually to do a question answering task, which immediately actually relates into the task that the hackathon is looking at. So for evaluating it for filling a knowledge base, we compared our results on the US NIST TAC knowledge base population task. So this is a task where you're wanting to get out facts such as somebody is somebody's spouse or somebody works for some company. And most of the systems that do that build large supervised relation extractors, training carefully on labeled data or databases of correct extractions. And we've built that kind of system as well, actually. But what we wanted to compare is that the University of Washington had also entered their open information extraction systems into this competition, and we hoped that by having the greatest semantic precision of natural logic that we could do somewhat better. And indeed we were able to. So the University of Washington system was able to get an F1 measure of about 19.6, which we were able to replicate doing it ourselves, which is always pleasing. And our naturally system was actually able to do somewhat better than that. And in particular, the right comparison is between these two systems, because the actual UW submission used an earlier open information extraction system and then also used some handwritten hacks to improve their precision, where the true comparison is sort of between OLI's precision and recall, and use of natural logic is actually kind of giving a noticeable bump in both of those. Of course, UW isn't the only person who can put in some hacks to improve precision and recall. We were able to add some bells and whistles onto our system and further improve its recall. Some of the getting better recall is things like being able to recognize names that are the same names, like Bob and Robert are likely to be the same. And so we're able to sort of actually produce a pure natural logic system that actually is doing pretty decently in the TAC KBP competition, better than the median entry in that competition, though still well below the best systems, which include our own best system. Okay, so that's OpenIE as natural logic, because really you can think of OpenIE as a sentence simplification task, and sentence simplification you can think of as doing natural logic. I guess I haven't updated this. This actually has now been released in Stanford CoreNLP, so the most recent 3.6 release of our NLP, open source NLP software. You can now ask for natural logic, positive negativity annotation, and open information extraction, and you'll actually then be able to get open information extraction triples coming off of sentences. Okay, so to learn natural language inference on real English, we need to teach a model English almost from scratch. And previously, there hasn't been a ton of data available for doing that. And so I just thought I'd mention one other new resource that we've built recently, is the Stanford Natural Language Inference Corpus, which is a very large supply of examples where we got Turkers to write sentences where they're pretending they were describing a photo and then making sentences that were either contradictory or consistent or inferable from another sentence. And so that's actually quite a nice new resource for testing models for natural language inference. Okay, so that's the end of what I was going to say. So that, the theme was how much effort should we do into making use of linguistic and knowledge representations for our inference. That some people have been trying to go extremely minimalist with, no knowledge representations. All we have for language is sequences. Sometimes then it starts to get a bit more complexified with memory and attention. I kind of feel that we want a little bit more than that, and that there is surely a right middle ground of simple representations that get at the central heart of language while not being overly complex. And I think the key to that is realizing that language and many other things does have this compositional structure where parts go together to build bigger parts. And so you get these kind of tree-structured models. And so I've been enthusiastic in the work that's been done on tree-structured or equivalently stacked neural networks. As you probably remember from some formal languages class, as soon as you have a stack, that gives you the equivalent power of trees. Lots of other good ideas, universal dependencies, natural logic inference, and going together that I think can be powerful ideas for leading to better natural language understanding and question answering systems. And indeed, in very recent work, we've actually been taking some of the ideas of that natural logic inference system and ourselves been applying it to some of the science question answering data of the same kind of the Allen AI Institute that you've been looking at in the hackathon.